Right then, worked answers for these 25 marks of electrochemical cells. Won't take long. Again, it's the explanations which are more useful than just ticking it or crossing it here. The mark scheme's on the teams, but I've got a paper copy here just for quick reference. So first of all, let's not waste time on what should be the easy parts. Ionic compound and what's the purpose of it? You can say to complete the circuit, potassium nitrate is always a safe bet. Okay, so we'll look at the mark scheme because, as I say, this is as much about understanding as confirming the answer. Allow complete the circuit, or ions can move between the cells, or accept maintain electrical neutrality. That's the idea that at one end positive ions are being formed or used up, and those new positive ions would need replacement, basically anions to come with. Or if the positive ions are being used up, then their counter ions are already in there. For example, if this was hydrochloric acid, some chloride ions, they need new partners to come out. So depending on which way current is flowing, with the standard hydrogen electrode, it might be right to left, depending on the E values. But essentially, like, these ions flow to balance the charges. Moving on. The examiner comments, I won't flash it up for here, it's worth reading them on this topic though. It mentions how a lot of students were writing that electrons flow through the salt bridge. That's complete nonsense. It's called the salt bridge. Salts are made of ions, not electrons, which can flow. The surface area of the platinum electrode doesn't affect the voltage. That's something we put in our notes. It would increase the current by reducing the resistance, or the amount of charge that can flow per second, but that's not something we have to study. We just look at the supply and demand, which is effectively the consequence. Voltage is the consequence of that. Now, this is all about using the SHE. We need to know about the SHE. One of the things is it always goes on the left. Fine, there it is. But the other thing is we should just know the formula for the half cell equation for this. So the standard hydrogen electrode is where 2H plus interchange between themselves and H2, and the half equation is as it's written there. Usually it's not written as reversible, but it could go in either direction, which is what that means here. So the reason I'm commenting on that is because they don't give us the other half cell. We're supposed to just know it. Okay, so here it is. We know also that by definition it's set as having an E value of 0. Let's see what we can do with that information in the next part. Now, again, for a multiple choice question, I've got quite a lot to say here because the examiner comments mention how few students got this multiple choice question correct. So knowing that the standard hydrogen electrode has this half cell with that E value, that allows us to work out, there's quite a lot of work to do for this mark, that allows us, from that we can work out that the spontaneous reaction, the one where E cell is positive, would involve the best reducing agent, which will be Mg, coming up against the BOA, the oxidizer in the more positive E, in this case it's just 0 rather than the other one being negative, which will be H+, okay? So the combination that will lead to a reaction is magnesium plus 2H+, gives Mg2 plus hydrogen. That's just the reaction for when you chuck a bit of magnesium into acid and it fizzes, okay, from GCSE. Now, the cell is set up back to front, but that's correct because this is the standard hydrogen electrode, it has to go on the left. But the more negative E should go on the left for E cell to be positive, and here it isn't, which means our cell's flipped back to front. That'll become relevant later on. So this would be the negative electrode, and that would be the positive electrode here, because that's minus 2.38, and that's 0. Okay, so just the relative charges, sign and value of the E values gives us our positive and negative, and it should be that the negative goes on the left, but the SHE is an exception that forces that to sometimes not be the case. Anyway, so the discharge reaction is magnesium plus H plus makes those. So how do we use that information to answer this multiple choice question? Well, they're asking us what would happen if we poured a load of water in. Well, pouring water in will dilute the magnesium 2 plus in solution. Now, magnesium 2 plus is a product of this cell reaction. And one of the things we said in class about changing conditions, namely concentration, on a cell voltage, is that we can apply Le Chatelier's principle. So even though we've correctly identified the BRA and the BOA as those two species there respectively, then this reaction is one way. It goes from the best and the best to their opposites, their worst and worst counterparts. But there is an equilibrium at both electrode. And so we can apply Le Chatelier's principle. Reducing the conc of magnesium 2 would shift the equilibrium at the magnesium electrode in such a way where we'd get more of this change happening, where magnesium atoms would fall off into solution. We could say in Le Chatelier terms to replace the magnesium 2 plus. And when that happens, electrons are left behind. Okay, so turning the page back again, that would mean that if we decrease the concentration of magnesium 2+, more Mgs will drop off to form Mg2+, and more E minuses, these are supposed to be little negative charges that I'm drawing, will build up there. So that will go from minus 2.38 to minus, I'm just making up a number now, so approach with caution, something more negative to a more negative E, meaning E cell would get bigger, albeit a bigger negative value here. So the EMF increases, meaning it becomes a bigger number. Now, again, the explanation wasn't needed here, but that's how we land on the conclusion without it just being a lucky dip that EMF increases. So to increase the voltage, you either increase the concentrations of anything in solution on the reactant side or decrease the concentration of anything on the product side for the cell reaction. Or in the case of gases, the equivalent to that would be changing its pressure increase or decrease. Okay, forward. Right, that was probably the one where there was the most to say all in one go. Give an equation for the overall reaction. So again, the exam report here says that most students wrote the opposite to that because they'd maybe missed or didn't realise they were supposed to think about the fact that the electrodes are back to front here because the SHE is the more positive, but it's still been put on the left. So again, it's just a reaction between magnesium and acid. That's a reaction that's well studied at GCSE, but I think students don't really ever realise that makes sense. Magnesium reacts with acid. We've never heard of H2 reacting with magnesium 2+, but maybe we just never told about it. Loads of working out here for this. The thing to watch out in this question, watch out for, is that they have got them in numerical order, but it's in ascending order. Normally, you've got more positive to more negative. Nonetheless, we know how to play this game. We're looking for the weakest oxidizer. So that'll be in the same equation as the best reducer, which will be the most negative E. So BRA is zinc. Worst oxidizer will be the flip of that, zinc 2. And on that note, the best oxidizer will be cobalt 3, and so the worst reducer will be its opposite, cobalt 2. Anyway, answer solved there, zinc 2+. Quote the conditions, 298 K, 1 molar of anything in solution. You can't talk about surface area of solids, there's no gases here, so that's all there is to say. And again, apparently lots of students got this back to front. That seems to be a theme in these questions when you read the examiner report. So 2 half cells have a difference. So there's 1 mark on the mark scheme for simply identifying that it must be to do with zinc and cobalt. Sorry, the zinc 2 half cell and the cobalt 2 cobalt half cell. And so I'm getting 1 mark just for having zinc, cobalt and their charges as well. The next mark is for putting them the right way around. So if you check the table on the other page, you'll see that the zinc has the more negative E, which means it goes on the left. It's the one where the BRA is, which means it's the one where oxidation happens because the BRA gets oxidized. As we read this left to right, you've got zinc turning into zinc 2 and cobalt 2 turning into cobalt. Again, mark scheme, it says correct order with phase boundaries and salt bridge. The salt bridge is the double line, the phase boundaries are these solid singles, no platinum. So if you put platinum, you can't have the second mark, even if you did put zinc 2, cobalt 2, cobalt. Double dash line, we're not going to do that. Extra phase boundaries loses. So the only way you could do an extra phase boundary here is if you put one at the ends, and that would lose you the mark. Okay. So you have a solid metal or conductor at either end. If it's not a metal, then it's graphite, which we haven't dealt with in class yet. There we are. Ignore state symbols, that's generous. Equation happening at the negative electrode. So the rules we apply, the more negative goes on the left. It's where the BRA is. It's the BRA that gets oxidized at the negative electrode, which is to say at the left-hand electrode. So that's where zinc turns into zinc 2 by yielding 2 electrons. Okay. Which species can react with water? The answer is cobalt 3+. We'll come back to these equations in a second. Let's just justify why that's the case. I won't spend too long on this bit. So which one can react with water? Okay, right. So we've already got the answer cobalt 3, but how do we land on that? Well, water only appears in this half equation, so it must be a reference to this O2, H+ and H2O1. And if we're going to get it, and therefore it's a reducing agent here because it's these are the equations we've been given. It's the only one that's got water in it, and water's on the right, so it's a reducer. So we need to pick a substance which is in a more positive E value. Because again, it's awkward because this is upside down. Usually the positives would be at the top. We're working upside down here. This is acting as the reducer. It's not the best out of the whole list, zinc is, but out of the series that we've got to pick from. And basically we need something on the other side of the coin which is in a more positive E. So my candidates are gold plus or cobalt 3 plus, because they are oxidizers in more positive E than the one that water's in as a reducer. Okay, so it has to be one of these 1.68 or 1.82. Again, check the phrasing of the question, which cobalt species. So it was going to be cobalt 2 or cobalt 3, and therefore it has to be cobalt 3. Gold plus would also do it. Gold plus would react with water. And then you can combine the half equations to get that. Oxidation products. Well, the element changing oxidation state is O. It's going from -2 in H2O to 0 in O2. Therefore, the oxidation product is the element that's got the O in it after oxidation, so that's O2. Okay, well done if you were catching all of that. Again, it's the phrasing here, and in Feb 26, when we're first looking at this class, we're going to be doing this very soon, as in like next lesson. How do we put into words our explanations for what can react with what or what can't? So there's only 2 marks here. This kind of terminology we'll come back to in a second. Why gold doesn't react in moist air. Now the moist air is a bit of a trap laid out, because moist obviously implies water. Air, well, oxygen really, isn't it? Let's be honest, is the active redox component of air. Nitrogen's famously unreactive, and we haven't got any half cell values that include N2 anyway. So it's going to be something to do with either the water or the oxygen. It's going to turn out to be the oxygen, okay? So why it doesn't react. Again, we're talking about gold AU. Need another coloured pen, I think now. Pencil it is. So there's AU. You'll have to bear with me because it's obviously a lot of scribbles already. And it is the subject of this question, why moist air and AU won't go together. So similar to what I've just done with water, my starting point is, okay, AU, what could react with it or what can't? It says does not react. So gold is a reducing agent here. So what would it react with? Well, it would react with any oxidizers for more positive E. So on this list here, the only thing that would react with AU apparently is cobalt 3 plus. That's quite interesting, I didn't know that. So gold can't react with water because they're both reducing agents in the data that we've been given to pick from. Air contains oxygen. Oxygen is an oxidizing agent, but the E values are the wrong way around. So if we were to couple up the gold and the oxygen stroke water half cells, the combination that would actually give a redox reaction would be the BOA AU plus going with the BRA H2O. So gold plus will react with water, therefore gold will not react with oxygen. Okay, so they wanted us to somehow recognise that was the case, which is why there's 1 mark for saying anything to the effect of gold can't reduce oxygen or oxygen can't oxidise gold. Let me show you the mark scheme for this one now. Yeah, oxygen can't oxidise gold or gold can't reduce oxygen, whichever way round in red and ox you want to go. Ignore references to water. It's moist, but the water's just not relevant because it's a reducing agent in the equations we've been given. Now, how do we explain this? How do we put that judgment into words? This is the thing we'll be practicing in class quite soon in Feb 26. So we can compare the E values, okay? So a nice efficient way to justify that would be to say, basically the E value of one is more positive or more negative than the E value of the other, and therefore what would happen is gold plus could oxidize H2O instead, or the E cell would be negative if we put it this way around. Again, there's a danger here that I could talk for a long time to make a reasonably short point, so this is something maybe we'll have to come back to it in class anyway. So if we just look at the 2 relevant half cells again, I've coupled them onto the margin here. As I said, the reaction that would take place is gold plus and H2O. So if I said something like the E value for the gold plus gold half cell, this is a notation that will be getting done in class very soon because we need to know it for these odd marks, 1 or 2 marks here and there. That's the more positive one, so I could say is greater than, which in this case means a bigger magnitude, same sign, so like more positive than the E value for the oxygen H2O half cell. Now that is just comparing the numbers, one's more positive than the other, but then we're allowed to take this leap and say, so gold can't reduce. We're kind of saying it would go that way, so can't reduce O2, or instead saying gold plus will oxidize H2O instead. Now again, let's just take one last look at the mark scheme in this video. How does that relate to what I've just said? the E value of one is less than the other, or that one is greater than. We're just comparing the numbers. That gets you the mark, just saying one's more positive or one's more negative than the other. That's enough. Or one's more negative, one's more positive, sorry. Or the idea that, you know, the E cell, this is a bit awkward now, would be negative. That's a bit waffly in my opinion. There's a better way of looking at it, just saying one's more positive than the other. Let's move on. That's probably as hard as it gets. Again, examine the comments saying how often, or it just says in the wrong places, but I think that probably means back to front. The nickel-cadmium cell, it's the positive numerical difference between them. That one's more negative, so it's the left-hand side. That one's more positive, so you get the voltage to be 1.4 volts. Quick tick and move on. When we combine these half cells then, so the more negative's got the BRA in it, it's the one that goes right to left, i.e. it goes as an oxidation itself. So the more positive, it's actually going to go left to right as a reduction of the Bohr. This equation needs doubling because there's only one electron in it. So that's one of the things you have to do here. And then once you splodge a cadmium, 2 hydroxides, two of that, nickel oxide hydroxide, 2 waters, and then on the other side of the arrow, 2 nickel hydroxides, 2 OH minuses, and 1 cadmium hydroxide, as I've done here. Once you put it all together, you should notice that the OH minuses cancel out. So you only get 1 mark if you don't cancel those out, I think. Again, I better check. Mark for the species. Okay, great. So that's basically writing all 5 of these. You get a tick where they're on the correct sides. Oh no, it says balanced. Hang on a sec. Oh yeah, right, deduct a mark for additional species. So there's 1 mark for that. There's then 1 mark for balancing it, but you'll lose that mark if hydroxide is shown. So if you've balanced the equation with 2, 2, 1, 2, 1, but then there's also 2 OHs and 1 OH minuses on both sides, you get 1 out of 2. The hydroxides have to cancel, otherwise you lose the mark. And the other mark was just for balancing it, which is to say don't forget to double one of the equations. Oxidizing agent, okay, so the Bohr is nickel oxide hydroxide. Again, it's the species which has an oxidation state change happen in it, in the nickel, in the more positive E. So it's the oxidizer. And that is an oxide ion, -2. That is an OH minus ion, which has a net charge of -1. Therefore, that must have been nickel 3+. We got oxide, OH minus, and that. You might be thinking, well, how was I supposed to know that was an oxide ion? Well, if nothing else, it was an oxygen atom in some form. We'd expect it to have a -2 oxidation state. So even if you thought it was covalent or whatever, it's still going to be -2. So the charges balance, or the oxidation states add up to 0. That's nickel 3. And then you've got a -2, a -2, and a +1, if you prefer. 1 mark per step. A couple of multiple choice questions. The answers go D, C, B, D. I'm going to go for each one. You decide if you still need to listen now. Hopefully you think it's worthwhile. I need to remind myself, I did these questions quite a long time ago. The EMF of that cell. Okay, so we literally read the silver one as the left-hand side electrode. We read that as the right-hand side electrode because that's how it's been presented to us. So we do right-hand side minus left-hand side, which is to say the lead to lead, minus 0.13, minus plus 0.8. So yeah, that's where D comes from, because we literally see, they've printed it on the left, so we assume that means the left-hand electrode. It does mean here, again, it's a back-to-front cell. E cell is negative because they've got their electrodes the wrong way around. Part 5, answer C, another changing conditions question. So again, we can just read this left to right, but the thing we need to check here is whether that's a back-to-front cell or not. These are awkward questions. So, and sure enough, this time 0 versus positive 0.8. Yeah, it's the SHE, which is why it's been put on the left. But this time it's also correct, if you like, for it to be the left-hand electrode because it's the more negative. So that tells me since E cell's positive, E cell is going to be 0.8 take away 0 equals positive 0.8. We can read this cell left to right, which is the normal, correct way. SHE is a bit of a spanner in the works. Sometimes it pushes it the wrong way around. So that tells me then that the reaction involves hydrogen and silver plus turning into H plus and silver. Now that equation isn't balanced. I'm not worrying about the electrons. I'm just looking at the chemicals for this multiple choice. So I could increase the voltage by increasing the pressure of hydrogen, by increasing the conc of Ag plus, or by decreasing the conc of H plus. Okay, and that therefore gives us answer C. We increase the reactants or we decrease the products. You can't do anything with a solid metal because there's nothing to be done with it. The surface area wouldn't affect it. If you wanted to decrease the voltage, the opposite of that, reduce the pressure of that, reduce the conc of that, increase the conc of H+. And they'd shift the cell equilibrium further in the wrong direction, i.e. the voltage decreasing direction. Right, 6, answer is B. How do we get here then? So if you got the answer B, good. Bear with me for a second, just for the last question, which is a bit awkward, and I was had to be quite methodical about it. So disproportionation, you know that's when an element undergoes simultaneous reduction and oxidation. And basically, it's either going to be the copper or the mercury electrodes that do that. Now, oh gosh, this is awkward. We conclude that only copper one does. Let's see how we get there. So first of all, I'm going to deal with the copper electrodes. Copper here, in the form of copper 1+. For a start, it does appear on both sides of the two respective half-cell equations. Because of the relative values, if we just couple up these two half cells, that's got the BRA in it. Oh, hang on, let me get this right. Yeah, so that's the BRA and that's the BOA. Now, the fact that the same species has both flags next to it tells us that can disproportionate. Two coppers would react with each other, copper 1+s, to make a copper 2 and a copper. Now we'll do the same thing with mercury, and the answer is no, it won't. So the more negative has the BRA in it, so that's liquid mercury. The more positive, that's mercury 2. So the combination that would go here is a mercury element and a mercury 2+ make 2 Hg+, which is like the opposite of disproportionation, because even though it's the same element, they're not actually the same species. Here it's two of the same thing, copper 1+. Yeah, right, brain hurting. Right, final question. I don't really want to have to go through this in painstaking detail. I don't think you do either. But it is important that we have a chance at understanding what the heck is going on here. So the answer is D. My scribbly working out might give you a clue. Which of these could reduce? They're giving us a number, so this must be something to do with molar ratio, which it is. So 0.012 moles of bromine. For a start, dichromate just can't take on bromine. I know it's getting a bit clipped off the top there. Bromine is an oxidizer, dichromate is too. There's no such thing as an ox-ox reaction, it's always redox, so dichromate can't touch it, so it can't be A. I almost picked B, then realised I'd made a mistake. I can't remember what that was, but I'll try and come back to it. C, something to do with the ratio I've written there. Okay, so the number of moles of vanadium 3+ is 0.012, so they'd be in a 1-to-1 ratio. So not 3. Okay, so then the question is, are they 1-to-1 in the half cell? Vanadium 3 could get oxidized, so bromine's up here. It's going to send vanadium 3 or iron 2 or sulfurous acid that way. So they would react, but this is a 2-electron half equation. That's a 1-electron half equation. So actually, a mole of bromine would take on 2 moles of vanadium 3+, and so 0.0212 would have 0.024. So that should be 0.024 mole of vanadium 3. You see the logic? I'm going to be a bit lazy now. I hope I'm not really disrupting you on this one. So using that idea of these will react. Oh no, they can't. So iron 3 can't react because it's also an oxidizer. No ox-ox, so that one's also out of the question. Answer's D. Sulfurous acid can be oxidized by bromine. There you go, I'm finishing it now. And also, look, they both have the same number of electrons, so 1 Br2 would take on 1 sulfurous acid, because when we combine these half equations, they'll still be 1-to-1, which is why the answer is D. You survived. Thank you for listening.